And we're off to the next unit, chemical kinetics, in other words, reaction rates. It's one of my favorite units. I think it's because we get to analyze data and pick it apart, and it's really just not that difficult. So what do we mean by kinetics? It's just the area of chemistry that is concerned with speeds or rates of reactions. The reaction rate, well, it's just how fast a reaction occurs. And the mechanism is a step-by-step molecular level view of a pathway. In other words, how exactly do the reactants become the products? Now, obviously, we can't see them, so we have guesses, and then they try to back that up with some data from experimentation. Again, we don't know for sure, but we can usually support it with some evidence. Let's just start with some basics. What are some things that can affect the reaction rate? Well, one is the physical state of the reactants. Are they homogeneous? In other words, are all of the reactants in the same state? They're all gas, they're all liquid, etc. Or are they heterogeneous? Are they in different phases? The more readily reactant molecules can collide with each other, the more rapidly they will react. So heterogeneous reactions are going to be slower than homogeneous. Increasing the surface area of a solid will make the reaction go faster because more of the molecules can collide with other molecules. Another thing that can affect the rate of reaction are the reactant concentrations. As reactant concentrations increase, the reaction goes faster because there's more likelihood that molecules are going to collide. I mean, just picture a classroom with 5 kids blindfolded walking around. How often are they going to bump into each other? Now let's put 100 people in a classroom blindfolded. How often are they going to walk around bumping into each other? So as you increase concentration, you're going to increase the number of collisions, which increases the rate of reaction. Reaction temperature. Well, as temperature goes up, reaction rates increase. Why? I think you know this. As the temperature goes up, molecules have more kinetic energy, so they're colliding more often with higher energy. And you probably recall from a basic chemistry class that in order for a reaction to occur, 2 things have to happen. Number 1, the molecules must collide with enough energy. And number 2, molecules must collide in the correct orientation. So higher temperature, faster moving molecules, more likely they're going to collide with enough energy in the right orientation. And the last thing is catalysts. Catalysts make the reactions go faster, and the catalysts are not consumed in the reaction. So the presence of a catalyst could affect the reaction rate. So let's look at the big picture one more time. The greater the frequency of collisions, the higher the reaction rate. What does it take to have a reaction? Well, they have to collide with enough energy to break bonds, and they also have to collide in the right orientation. In regular chemistry, I had you guys line up, and I said, well, we want that Br and that Br to be able to hook together and become Br2. But the way we lined up is we had the Brs at the end of the molecules. Well, imagine 2 oncoming trains collide. The 2 engines are going to connect together, but the cabooses are too far apart. So obviously they have to line up in a way to make the 2 cabooses, in this case, connect together. By the way, there are some supplemental videos in modules. One is on equilibrium, which kind of has to do with this unit, but really it kind of gets into that whole orientation thing. And then, of course, how to get a date for the dance. Definitely check that out again. Reaction rate is kind of like speed. When you're driving, it's how far do you go in a certain amount of time. For reaction rates, it's the change in concentration of reactants or products per unit of time. Normally, our units are molarity per second, although it could be molarity per hour. It could be a variety of things, usually molarity per second. Again, change in molarity over change in time. We use the brackets to say concentration. So if you see bracket NaOH, remember we're saying the concentration of NaOH. And from here on out, I use brackets all the time with nothing inside just to mean concentration. Now, when you're finding the change in concentration, remember that you always begin with the final number and subtract the initial number. This is important because if your answer is negative, it means that your concentration is decreasing. If your change is positive, it's increasing. And that's important because if something is decreasing, it's probably a reactant being used up. If the rate is increasing, it's because you're probably making it as a product. And if you were to graph this on a graph, you're going to see here on the next slide that a lot of times it's not linear, it's actually a curve. And that's because initially you have all these reactants reacting together. Well, as they start getting used up, those collisions become less frequent, and that will actually lower the reaction rate. So typically when we're talking about reaction rate, we're talking about the initial reaction rate, right at the very beginning when you have all those reactants in a high amount of concentration. You're going to see the instantaneous rate quite a bit. An instantaneous rate is just the rate at a particular moment in time in a reaction. And you can actually determine that from the slope of the curve at a particular point in time, which does sound a little bit like calculus. And you actually can do calculus here, or you can do what they show you on this graph, which is make a triangle out of it and do a little bit of division. We're not really going to get into that. I just want you to know that throughout the chapter when you're reading in the textbook, when they talk about rate, they're talking about instantaneous rate. What is that rate at a particular moment in time? So what's the big deal about average versus instantaneous rate? Well, let's talk about driving for a moment. If you were to drive from Worland, Wyoming to Cody, Wyoming, which is 90 miles, in 2 hours, your average rate would be about 45 miles per hour. But the instantaneous rate is that moment in time. Were you at some moment in time maybe going 80 miles an hour to get around somebody? Was there that moment in time that you had to slow down to a crawl because there was a deer on the road? So your instantaneous rate is that split moment in time, while your average is just an average over the whole time period. Let me clear something up. You can find the rate at which a reactant or a product changes. You can also find the rate for the whole reaction. The rate for the reaction is the same as the rate for an individual reactant or product that has a coefficient of 1 in the equation. So what if you have a balanced equation and nobody has a coefficient of 1? How do you find the rate for the whole reaction? It's actually easier than you think. Find the rate of reaction, change in concentration divided by change in time. And then what you want to do is you want to multiply it by 1 divided by the coefficient. Now you'll notice that for the reactants, we're multiplying by a -1, and we're not doing that with the products. Well, the rate of reaction for all products is always positive because we're making them, we're increasing them, while the reactants are always negative because they're decreasing. You do not want the rate of a reaction, not the rate of a individual chemical, the rate of the reaction to be negative. You want the rate of the reaction to be positive. So that's why we multiply by the -1 for the reactants. Or I just tell students to do like the absolute value. Just ignore any negative signs. Does that make sense? All right. So now we know how to find the rate of the reaction or the rate of change for something in a reaction, a reactant or a product. Now we're getting into something called the rate law. And the rate law really is just an explanation of how concentration can affect the overall rate. It's really what it is. So when you write the rate law, it takes the generic form of rate equals K. K is just a constant. And then concentration of the first reactant to an exponent, concentration of the next reactant to an exponent. We're only dealing with the reactants. We don't care about anything else. The magnitude of K, that constant, does change with temperature. So a lot of times you'll see in problems at such and such temperature, blah, 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 blah. You don't need the temperature necessarily in the math. It's just so that you know at that temperature, that is what K would be. Change the temperature, new value of K. And the exponents are always small whole numbers. Well, I have seen cases where they weren't whole numbers, but we're going to go with whole numbers. So let's take a little bit more time and talk about the rate law and reaction orders. In the rate law, the exponents are not called exponents, they are called reaction orders, an order of 1, an order of 2, and then to find the overall reaction order, you just add up the exponents. Pretty straightforward, pretty easy. The exponents indicate how the rate is affected by each reactant concentration. For example, if something has an order of 1, that means you have concentration to the 1. If you double the concentration, the reaction rate doubles. So if you put a 2 in here and it's to the 1 power, 2 to the 1 is 2. Double the concentration, double the rate. But what if you have an order of 2? In other words, you're squaring it. Well, if you double the concentration, 2 squared is 4. You will quadruple the reaction rate. Exponents are found experimentally. I'll show you that in a second. And most of the time, we are only dealing with reaction orders of 0, 1, and 2. Anything above that just is very rare. It doesn't happen very often. The little value of K, that constant, can actually tell us how fast or slow a reaction is. If it's a really big, large K value, like 10 to the 9th or higher, it is a fast reaction. If it's just 10 to the 1 or lower, it's going to be very slow. The units for K, the label you put on it, well, they change all the time. And it depends upon the overall order of the rate law, which I'll show you here in an example. It's really not hard, and you learned it in basic chemistry. The rates of a reaction depend upon concentration, and the rate constant depends upon temperature and catalyst. For the most part, we don't really deal with all that. I just want you to know how to analyze the data and come up with the rate law, which we're going to take a look at. Let's look at an example. It says the initial rate of a reaction A plus B makes C was measured for several different starting concentrations of A and B, and here are the results. So what you'll notice is you have 3 trials right there. You'll notice that you have concentration of A, concentration of B, and then the initial rates. What this problem wants us to do are 3 things, and we'll tackle them one at a time. First is just write the rate law. So we know it's going to be rate equals, I apologize, I don't have a mouse. Don't laugh at me too badly. Rate equals K, and then it's going to be concentration of A and the concentration of B. But we need to find those exponents, and this is all done from experimental data. So here we go. Let's take a look at this. What you want to do is you want to evaluate A when A is changing but not B, and when B is changing but not A. Because think about it, if you change 2 things at one time and the rate changes, well, was it because of A? Was it because of B? Was it because of A and B? We don't know. So in science, we change one variable at a time. So if you look at A, A changes from 1 to 3, but notice that B did not. It was still 0.1, 0.1. So all we're changing is A. So here is what I do. This is how I do it to find that exponent. I say, okay, well, 0.2 divided by 0.1 is 2. So in other words, the concentration doubled. Well, what did the rate do between trials 1 and 3? Well, 16 divided by 4 is 4. And I literally will write this on a piece of paper just so I can see it. And then I ask myself, okay, well, what exponent gets me from 2 to 4? 2. So A has an order of 2. If you double the concentration, the rate will quadruple. That's hard to say. So now let's look at B. Where does B change but A doesn't? Between trials 1 and 2. It goes from 0.1 to 0.2, but A did not change. So again, what happened here? Well, we doubled the concentration, but what did the rate do? Well, 4 divided by 4 is 1. What exponent is going to make 2 become a 1? 0. So it has an order of 0. And what does that mean? It means you can dump in the entire box of B, and it is not going to change the rate at all. So our rate law can actually be written without this piece at all. The rate law is simply going to be R equals K bracket A bracket squared. In other words, the rate only depends upon A. All right, so now that we have the rate law, we can find the rate constant. And you'll see here on your screen that this is the rate law from the previous slide. Well, how do we find the value for K? Just take any one of those 3 trials and plug in the values. I always take the first trial so that I can read straight across. Otherwise, I'm old, my eyes kind of get messed up. So where did I get these values? Well, the initial rate is 4 times 10 to the negative 5th equals K times the concentration of A, 0.1, and don't forget to square it. Our rate law says to square it, so you have to square it. Now, why is B not included? Because remember, it has an order of 0. It does not matter. And you just do a little bit of algebra. So 4.0 times 10 to the negative 5th divided by 0.1 squared, and you get this for K. Now, where did I get that crazy label? Well, let's remember that the rate R is molarity per second, okay? And I write my little s's cursive, otherwise they look like 5s. So the label for K has to multiply by this and cancel out to get molarity per second. Well, what is 0.1? That's molarity. Molarity squared, right? So over here, A has a label of molarity squared. Well, what do you need to multiply by so that all you have is one M and an S underneath? You guys are always going to have an S down here. Always. Always, 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 always. And the rule is, and this is always going to be a 1, the rule is you're going to have 1 less the M than the total. So our total is a 2. So I'm just going to have 1M right here. And so this right here is the label. And you could write it like that, but I'm just going to simplify something. Let's just say our number was 4. 4, 1 over ms just looks really bizarre. See, look at that. Isn't that kind of crazy? Even with my crappy handed finger mouse. So what we do instead is we write it like this. M to the negative 1, S to the negative 1. So what if you had an overall order of just 1? So this piece right here would just be an M, right? Well, you wouldn't have to have an M on the bottom. So your K would just simply be S to the negative 1. If you had an order of 4, you would have M to the negative 3, S to the negative 1. So always an S to the negative 1, and the M is 1 less than the total. Well, the last part of this problem is, all right, well, find the rate when concentration is that. So you just take your entire rate law. Now notice the only thing I did differently is I actually put in the value of K, and you just solve. So what if A is 0.05 instead? Again, I don't care about B, it's not part of the rate law. Just do your math and you get that, 1 times 10 to the negative 5th. And rate is going to be molarity per second. And if you don't believe me, it even says it right there in the data table. So let's just talk briefly about the difference between a first order, a second order, and a zero order reaction. First order is just what it sounds like. It depends upon the concentration of only one reactant to the first power. And luckily we have people who enjoy calculus, and they can actually take something called the integrated rate law. Now we're not going to use this too much in our class, but we can use this equation to find the concentration of a reactant remaining at any time after the reaction has begun. Kind of cool. We could look at the time interval required for a given fraction of a sample to react, or the time interval required for a reactant concentration to fall to a certain level. What I want you to take away from a first order reaction is that you can use this equation and actually do something kind of cool with a graph. So if you take a look at this equation right here, notice that this is y, This is slope. Time is going to be your x-axis, and then, the y-intercept b. So what does this mean? If you graph, say you do a reaction, you have data. If you graph the natural log versus the time, and you get a straight line with a slope of negative k, then it is first order. And this is actually a concept we're going to use when we do our crystal violet lab. You're going to run a reaction using the spectrophotometer, and you're going to graph a bunch of things. You're going to graph just the absorbance, you're going to graph the natural log, you're going to graph a bunch of different things, and you're going to find that when you graph the natural log of the concentration against time, you get a straight line, you get a first order. And I'll show you how the graph differs for second order as well. Recall what second order means. It either means you have one reactant to the first power times another reactant to the first power, or you just have one reactant squared. Either way, your overall rate reaction order is 2. Calculus, you get this integrated rate law. So in other words, if you graph the inverse of the concentration, you get a straight line. So in the crystal violet lab that we do, if you're going to do all these graphs, if you graph the inverse, so 1 divided by the concentration, and you get a straight line, you're going to know that the reaction was second order. Again, if you do the natural log against time and you get a straight line, it's going to be first order. Remember that. Zero order, it occurs when the rate of disappearance of A is independent of the concentration of A. In other words, the rate has nothing to do with the concentration of that particular chemical. I mean, imagine you have a box of this chemical and you just dump the whole thing in. It's not going to make the reaction go any faster. That is zero order. So when you do the integrated rate law, you get that equation. And what that means, again, if you think about the fact that this thing right here is y, if you graph the concentration versus time and you get a straight line, it's a zero order. And when would you have this? One example would be when a gas undergoes decomposition on the surface of a solid. Just quickly, let's review again. If you graph the concentration versus time and you get a straight line, it's 0. Natural log of the concentration versus time, first order. The inverse of the concentration, second order. Seriously, memorize this. You'll need to know it for the test. If you ever take an AP test, you'll see this. For example, they'll just give you a graph and say, well, what's the order of the reaction? You're going to be like, dude, seriously, it's a graph. Well, if it's the natural log and it gives you a straight line, first order. We can't talk about reaction rates without discussing half-life. And this is just the time required for the concentration of a reaction to reach half of its initial value. So this is especially convenient with first-order reactions. A fast reaction has a very short half-life. This is applicable in carbon dating, pharmacokinetics, drugs and interactions and how they work in the body. There's so many reasons why this is applicable. But that's the equation. We will use it a little bit. But in a first-order reaction, the concentration of the reactant decreases by 1/2 in each of a series of regularly spaced time intervals. So say you start with 100. In, let's just say an hour, you're going to have half of that. Well, that would be 50. In another hour, you'd be down to 25. Then you'd be down to 12.5. And then you'd be down to, I think you get the point. The math there, that equation makes life really easy. Let's take a moment and revisit temperature and rate just one more time. So the collision model says that molecules must collide to react. The greater the number of collisions per second, the greater the reaction rate. And as the concentration increases, the number of collisions are going to increase, and therefore the reaction rate will increase. Well, if you increase the temperature, particles have a faster speed. They're going to move faster. They're going to collide more often, more forcefully, meaning with enough energy in the right orientation, and reaction rate's going to increase. And don't forget about the orientation factor. They have to collide in the right orientation in order for a reaction to occur. So just because two things bump into each other doesn't mean you get a reaction. And activation energy is simply the minimum energy required to start a chemical reaction. And if you haven't yet gone and watched the how to speed up the rate of a reaction, how to get a date for the dance, really is a great analogy that shows you why all these things are important. Let's review this energy diagram and talk about activation energy. Again, the activation energy is the energy required to get a reaction started because you need energy to stretch, bend, and ultimately break bonds. And this usually comes from the kinetic energy of the colliding molecules. When you look at this graph, this is where we are starting. So those are your reactants. From here to the top of the hill, so it's like climbing on a roller coaster, that's the activation energy. That's the amount of energy needed to get the ball rolling. And then up here is what we call the activated complex. We know that these reactants change shape and become some glob thing before they become the product. We just don't know for sure what it is, but we call it the activated complex, and we think we know what it looks like, again, based on theory and some experimentation. And then down here is where we end. These are the products. So let's review this. We started here and we ended here. So how do you know if it's exothermic or endothermic? Well, you need to look at the change in energy. And remember, we always do final minus initial. Well, don't we end lower than we started? Isn't it losing energy? Exothermic. So in endothermic, it's going to look something like this. You're going to have that hill, but then you're going to end higher than you started. That would be endothermic. So the rate depends on the magnitude of the activation energy. That's E with a little a. Obviously, a smaller hill, faster reaction. Bigger hill, it's going to take longer. And remember, in regular chemistry, we talked about how these reactions a lot of times go forward and reverse. So in the forward direction, not a super big hill, but if you go in the reverse direction, a much bigger hill. So it's going to take a lot more to get that reaction going. So up to this point, to find the rate law, we had to analyze some data. When did A change but B didn't? What did the rate do? When did B change and A didn't? What did the rate do? Well, if you have a reaction mechanism and you know the slow step, you can write the rate law based off of that. So what a mechanism is simply a series of reactions that explains how we think the reaction proceeds. This becomes that, and then that becomes this, and then this becomes that, until finally you're at the end. Obviously, we don't know for sure how it happens, but we do back it up with all sorts of experimentation. So a mechanism will describe the order in which bonds are broken and formed, changes in the relative positions of atoms. The atom was over here, now it's over here. And when we say elementary reaction, we're just talking about a single step in a mechanism. You can also talk about something called the molecularity of the reaction, and it's just simply the number of molecules that participate. Unimolecular just means you have one molecule. Bimolecular, you have two. Termolecular refers to three. And believe it or not, 3 molecules is pretty rare. So we don't usually talk about something beyond a termolecular, because think about it. What is the likelihood that 3 molecules will collide in just the right orientation with just the right amount of energy? Not very likely. So most mechanisms have more than one step, and you can do a reaction diagram as you see over here, and you're going to see several different humps or bumps, and that's just however many bumps is how many reactions you have. So this one would have 2 steps in it. Just to note, if you have all those elementary reactions, if you were to add them up algebraically, you should get the overall process. And when you do that, you'll notice that, so you've got all these equations. Well, sometimes you have things on this side and this side of the arrow. If you find the same thing on both different sides, just like in algebra, we cross them off. So this is how you can identify intermediates and then catalysts. An intermediate is something that is formed and then immediately used. So say you've got the first step, A plus B makes C, and then you have C plus X makes whatever. That C was just made and it's just being used. That is an intermediate. You make it, you immediately use it. Okay, they're not the same thing as a transition state. Those are unstable molecules and can never be isolated. But I do want to warn you that if you're writing a rate law, you cannot include an intermediate in the rate law, and I'll show you what you need to do about that. Rate laws are found experimentally. And if a reaction is elementary, that's just one step in a mechanism, the rate law can be based directly upon that and its molecularity. Unimolecular processes are always first order because it's just one thing. Bimolecular is going to be second order because there's two things. And if you look at that chart, those are all the different options you can get for uni, bi, and termolecular. Again, termolecular, very rare, not very likely that three molecules are going to collide in the right orientation with enough energy. But it's pretty easy to write a rate law from that slow step. So again, a rate determining step, i.e. that is the slow step, it's the one that dictates the rate law. The coefficients become the exponents. So each step of the mechanism has its own rate constant, its own activation energy. The slowest step is going to determine how fast the overall reaction goes. And it really doesn't matter if you make everything else faster. If that slow step doesn't improve, it's just not going to change the overall rate of the reaction. Think about a relay. You've got three super fast swimmers, and the fourth one is just slower than molasses in winter. Well, if the other three continue to get faster, but that fourth one doesn't, it's really not going to change the overall rate of that relay team. So what you want to do is you want to look at all the elementary steps, and if you can identify the slow one, again, that becomes the rate law. But they do still, scientists that is, they do still compare this to observations from actual experiments to back up that, yeah, we do think we have the right mechanism. We do think we have the right rate determining step. Now, is there possibly another mechanism? Yeah, probably. Do we know for sure? Of course not. Now, when the first step is the slow step, easy. That's your rate law. You just write it. The problem is when the fast step comes before the slow one, because now your slow reaction probably has an intermediate in it, and you can't have an intermediate in the rate law. But if you go back to that first step, that fast step, instead of an arrow, just read that arrow like an equal sign. So this side equals this. So you might have like a squared equals c. Well, c is your intermediate. So down here in the slow step where you have c, you can just replace c with that a squared. And we will practice this in a problem. It's just a little bit of algebra. It's really not that hard. Just know that an intermediate cannot be in a rate law. All right, I know this is kind of long, but I promise we're almost done. Catalysts and just application of catalysts. A catalyst is just a substance that makes the reaction go faster. The catalyst is not used up in a reaction, so if you're looking at a mechanism, you will start with the catalyst, and then at the very, very end, no matter how many steps you have, it'll be there at the very, very end. So it does cross off. You don't see it in the overall reaction, but it never changes. It's there in the beginning, it's there again at the end. A lot of times when you're writing a reaction, over the arrow, we will write platinum or whatever the catalyst might be. We use catalysts all the time in the human body. If it weren't for catalysts, we wouldn't be alive. They're in the atmosphere, they're in the oceans, just chemical reactions everywhere require catalysts. A homogeneous catalyst simply means that the catalyst is in the same phase as the reactants. How do they work? Well, we do believe it provides a different mechanism that decreases the activation energy. Some people say it's like that matchmaker, and it actually takes this and it takes this and it brings them together in that right orientation, which lowers the activation energy. But the basic idea is that it makes the reaction faster, it lowers the activation energy. Now, a heterogeneous catalyst is one that is not in the same phase, and you did this in basic chemistry. You took hydrogen peroxide and poured it into a beaker. Nothing happened. The moment you added yeast, the hydrogen peroxide broke down. So yeast was a solid, the hydrogen peroxide was a liquid. So the yeast, by the way, is the catalyst. That would be a heterogeneous catalyst. The initial step in a heterogeneous catalyst is usually adsorption, which simply refers to the binding of a molecule to a solid surface. And in that case, the surface area of that catalyst does become an important factor. In the human body, we call catalysts enzymes, and they are large protein molecules with really large molecular weights. And enzymes have an active site. That is where the reaction actually occurs, and they can change shape as it binds to the substrate. Intermolecular forces. Substrates are the substances that react at the active site. It's kind of like a lock and key model. The substrate fits into the enzyme just right, and they're pretty cool. If you take AP Bio, you will get way more into these than we're going to get into it here or in biochemistry. But the enzyme speeds up the reaction rate. Now, there is something called an inhibitor, and it will bind to the active site, which stops the other chemicals and enzymes and whatnot from binding, whatever needs to bind. Sometimes they're really kind of complicated. And so an inhibitor is just that. It inhibits the reaction and it slows down the rate.